Alright, so these are some partial solutions to this third module on MATLAB for MAT 290, and I'll include and discuss some of this solutions for each part, just to give you an idea of how you might approach them. So the first part of this module deals with numeric integration, and specifically using this quad-L function in MATLAB, which is one of the built-in tools for integration. And this quad-L function relies on a user-defined function which defines the integrand. So you can define this function either as a M file or as an inline function, and either one would be fine. So in considering these integrals that are given in the exercise, let's think about this one and try to evaluate this in MATLAB. So in MATLAB we can define this integrand using an inline function. So we'll define this integrand to be x raised to the 5 times x raised to 2 plus 1 all raised to the 0.5. And defining that this is a function of x. And so you have to notice, of course, that we use the dot operators to evaluate this. So this defines this inline function. And then I can use the quad-L function to call this inline function. And since it's an inline function, we will use this syntax and evaluate this from 0 to the square root of 3. And so we get this numeric answer out of it. So this is the area under this integrand function from 0 to the square root of 3. So this then has this value of that we can find from MATLAB. And similarly, you can define the other integrands in the same way and calculate these integrals using this quad-L function. Now the second exercise deals with a improper integral, this where the limit is infinite, and so we can actually evaluate this using the quad-L function by extending the upper limit to be very large numbers and see if we find a limiting value. So in MATLAB you would approach this in the same way, where you could say redefine our integrand function and then use the quad-L in the same way. So again, it's a function of x, and so we'll integrate, say, from 0 to 3, and we need to multiply this by a factor of 2 since we're integrating only from 0 to 3. So we can see what that value is, and then if we integrate from 0 to 10, we can see that there is this bit of convergence to a specific number, and we could formalize this by putting this inside a for loop. Say let's integrate over these first 30 terms and calculate this integrand for each value of e, and what we get out of it is this vector q, and so this is for this upper limit of 0 to 1, 0 to 2, 0 to up to 30. And so if we wanted to plot this, we could plot this as 1 to 30, so that's our vector representing the upper limit, and q, and what we see is that there's definitely this very distinct value at which this integrand converges. And really you only need an upper limit of 2, 3, or 4 to find that this limit converges. So if you look at this specific number, So we get this about 1.7725. And so this has a very nice relationship to a very famous geometric parameter of math. So, but you can see that you can still evaluate these improper integrals by just extending this upper limit and seeing if there's a point where it converges. So this last part of this numeric integration exercise deals with Fourier series expansion, and this is a very interesting idea where you can expand any periodic function f of t in terms of a collection of sine waves, and these sine waves are built upon a single or a fundamental period. This is omega naught, or fundamental frequency omega naught, and n is this multiple of this fundamental frequency. So essentially what we're doing is we're creating this periodic function f of t by adding up a series of sine waves which are related to each other. And the coefficients of each of these sine waves, or each of these harmonics as they're called because they're all related to a single frequency, can be given by this integration. And so we can evaluate this integral for different values of n using this numeric integration approach. So the first part asks you to find this Fourier series expansion, which means calculate these coefficients, b, for the first 21 harmonics. So basically n ranges from 0 to 20, and our fundamental frequency is related to the fundamental period t0, which is 4 seconds. So this is the period of the original periodic function f of t, and that's how we build up this Fourier series. So to do this in MATLAB, you can take a look at or create a little function called these Fourier coefficients, where we've defined an inline function which has the f of t, and so this is the integrand of the calculation of the coefficients. So we have sine n 2 pi t divided by t naught. So t naught represents this fundamental period, and so our omega naught is given as this 2 pi t naught. So this inline function that I've defined is just defining this integrand. So this defines the inline function, and to it I pass the variable of integration, which is t, the n, which is the coefficient of the expansion that I'm looking for, and then the fundamental period. What is that fundamental period? And then my bn is just an evaluation of that integral, so it's this 2 over t naught times the result of that integral, where I'm integrating with respect to t, and I'm also passing the variables n and t naught into my integrand, and I'm evaluating this from minus t over 2 to t naught over 2. So this is this calculation, and now I've automated it so that I can do this for any value of n. So I've created a script which defines the fundamental period, t naught, as 4 seconds, and I've created a vector which represents which of the coefficients I'd like to find. And so I'd like to find the first 21 harmonic, or the first 21 coefficients, so this is n ranging from 0 to 20. So this for loop calls this Fourier coefficient function to calculate the coefficient through this integration of each of these harmonics. And then this last for loop recreates the time domain function by creating a time variable or vector from minus 8t0 to 8t0. And so then f of t is created using this summation of these coefficients times these sine sinusoidal signals, and this is calculated at each value of t. So this for loop runs through time and calculates this f of t at each value. And so at each value of t, it does a summation. And that's what this function is saying, is that for each value of t, we do this summation, and ideally we'd have an infinite number of terms, but in this case we're only having using the first 21 terms. And then the last two parts of this script is to plot both the time domain function as well as the values of the coefficients. So if I run this script, I get two plots. So this is the values of the coefficients. So these are B0, B1, B2, B3, B4, etc. So you can see that as you go to higher harmonics, the sine waves are becoming have a higher and higher frequency. The coefficients are dropping. And also you can see the coefficients oscillate between positive and negative. Now in the time domain, between minus 8 seconds and 8 seconds, you can see that these 21 harmonics summed together produce a very nice replication of my periodic ramp function with a fundamental period of 4 and a value of plus or minus, or peak values of plus or minus 2 volts, or 2. So this is quite nice. And now I can change this. The second part asks you to, or the third part asks you to consider only the these parts of the summation, or these terms of the summation. So when n is equal to 1, when n is 5, when n is 10, when n is 15. So I can run this script again, and now you can see the version of the time domain function which I get is quite a poor representation of my periodic ramp function. And you can see the ripples which indicate that this is a collection of sine waves. We're really collecting these oscillating waves using the particular recipe given by the coefficient values. And then I can extend this. So instead of just thinking of these 4, I could say let's think about the first 50 terms, or 51 terms, and then run this. And it takes a little while because we're doing a 50 integrals, and then we're doing 50 summations, or more than that, sorry, over 1,000 summations for every point of time we're doing these summations. So here you can see these are the first 51 coefficients from 0 to 50, and as we go to higher values of n, the coefficients drop off, and you can see that we're starting to get nicer or smoother ramp functions in the middle, but the ends are still somewhat incorrect. And that's because we're really limiting the number of coefficients which we're using. But we do see that the main ramp function is getting less wavy, which is a good sign.